All right, everyone. We have a car, let's say, that's just sitting on the road right here. There's the car. You like my car? Look at this. It's even better. It's even better if I put brake light on it. Or maybe I can even put a headlight on it up there. Now, do you like it? All right. That car is sitting there anyways, at rest. At 0 meters per second is its speed. It's waiting for a stoplight to turn green, or it's waiting for something, right? Car's sitting there. Car comes up from behind and hits it. What happens to this car as a result of being hit? What happens to this car as a result of being hit? Good. Right now, it's in what we call static equilibrium. It's not moving. The forces acting on it are balanced. There are forces acting on it. You may not realize that right now, but there are forces acting on that car right now, even as it sits there at rest. But they're balanced. As the car comes up from behind and hits it, it's no longer in static equilibrium. It's no longer at rest, and the forces are no longer balanced. There's an unbalanced force acting on it, and when an unbalanced force acts on it, it causes it to accelerate. Okay? In other words, its motion changes. Okay? An unbalanced force can cause motion. We said an unbalanced force can cause acceleration, right? Okay. Well, it causes it to speed up here. What about if the car is moving? Okay, what about if it's moving at, let's say, 10 meters per second? Describe the motion of this car or describe the term, give me the term that describes the motion of this car when it's moving at a constant speed of 10 meters per second. 30 seconds ago, this car was in static equilibrium because it was at rest and the forces acting on it were balanced. Now it's what? It's not in static equilibrium anymore, right? Because it's not at rest. Are the forces balanced acting on it? It's moving at a constant speed. Are the forces balanced? Yes, the forces are balanced. If the forces weren't balanced, what would happen to the car? Well, it would, go ahead. Right. It wouldn't be moving at a constant speed. It would either speed up, or it would slow down, or it would change direction. But it isn't. It's moving at a constant velocity of 10 meters per second. The forces are balanced acting on it. What term do we assign to this car as it's moving at a constant speed when the forces are balanced? Carrie? Translational equilibrium. Good. Translational equilibrium. So when forces are balanced, it's in equilibrium. When it's at rest, it's static equilibrium. When it's moving, it's in translational equilibrium. Does that make sense? Let's just reiterate Newton's first law again, just for 1 second here, which kind of goes to describing what we just talked about. First part of Newton's law says an object at rest will do what? Bart, an object at rest will do what? Good. Good, until an unbalanced force acts on it. Perfect. Okay, an object in motion will do what? An object in motion will do what, Allie? Good, it's going to stay moving until an unbalanced force acts on it. But it's going to stay moving specifically at a constant speed and in a straight line. So you're traveling down the highway, you might be turning around, going around turns, going around corners. Okay, you might be speeding up, you might be slowing down. There's got to be unbalanced forces causing all of that. If you're going at a constant speed, and let's say you hit a patch of ice, you're going to keep going at that constant speed, and you're going to go in a straight line. No longer are you going to be able to make that turn, because Newton's first law says an object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. All right, here's a new question. What does kind of a new question. What does acceleration depend on? I'll give you a hint. It goes back to inertia. At least part of it goes back to inertia. You guys remember what inertia was? Don't answer that question right now. It's kind of rhetorical. Okay. Remember what inertia is. What does acceleration depend upon? Give me one thing, Jacob. Depends on mass, yes. The heavier something is, the less something will accelerate. Let's look at the extremes here, okay? You got a little brother on a tricycle. Okay, your little brother weighs 30 pounds. His tricycle weighs 10 pounds. Total of 40 pounds. You push your little brother on that tricycle with a certain force. Then you try pushing a car with the same force. A car which has a mass of about 2,000 kilograms. Which will accelerate more? Your little brother on the tricycle or the car? Which accelerates more with the same force? Obviously, it's the brother on the bicycle, right? Because that person, that brother on the bicycle has less mass. The less mass something has, the easier it is to accelerate. The same force will cause less mass to accelerate more. So what's it depend upon? Mass. But it's not a linear relationship, right? Because as mass goes up, the acceleration goes down. What else does it depend upon? Bart? Force. Good. The net force. Not just force, but the net or the unbalanced force. How does that affect it? Well, let's take the car. You push a car with a little bit of force. You cause that car to accelerate because the car is not a very heavy car. You push it with a force that's twice as big. What happens to the car? Does it accelerate more or less? More. So in other words, the more force you have, the more acceleration you have. As mass goes up, acceleration goes down. As force goes up, acceleration goes up. Newton's second law tells us exactly that. That the acceleration of an object is directly related to or directly proportional to the net force. In other words, as force goes up, acceleration goes up. As force goes down, acceleration goes down. It's directly proportional to the net force and in the same direction. So as force goes up, acceleration goes up. As force goes down, the acceleration goes down. But if the force is to the right, the acceleration will also be to the right. If the force is to the left, the acceleration will also be to the left. The acceleration of an object is directly proportional to the net force and in the same direction, and inversely proportional to. Inversely means as one goes up, the other one goes down. Fill in the blank there. It's inversely proportional to what? As something goes up, the acceleration goes down. No. Not gravity. Mass. Inversely proportional to the mass. In other words, if we write this as an equation, as F goes up, A goes up. As M goes up, A goes down. In other words, A is equal to F over M. The acceleration is equal to force over mass, the net force over the mass. Usually, however, we see that rearranged to take this form, F is equal to M times A. And in fact, this is the way that it appears on your data sheet, F is equal to M times A. Newton's first law talks about what happens when there are no unbalanced forces acting on the object. Newton's second law tells us what happens when there are unbalanced forces acting on the object. In other words, Newton's first law involves constant velocity, right? Equilibrium, either static equilibrium or translational equilibrium. Newton's second law involves acceleration. Yep. Yep. Yeah, the little arrow still means vector, so that means that acceleration is a vector. Of course, we knew that from our last unit in kinematics, right? But force is also a vector because, of course, the acceleration is in the same direction as the force. So if there's a direction associated with acceleration, there's got to be a direction associated with force as well, so it's got to be a vector. So a new equation. This is our seventh equation now. Right, we learned a group A equation, V is equal to delta D over delta T. Then we learned 5 group B equations, right, involving acceleration. Now we've got another one. Which category should we put this one into, group A or group B? Yep, this is a group B equation. Yeah. So whenever we're doing a problem involving acceleration, we now have one more equation that we're allowed to use. That was applicable in all the problems that you did involving Group B in Unit 1. It just wasn't relevant. It just wasn't helpful in all the problems you did in Unit 1. But it was applicable. It was valid. Okay, it's valid anytime you have a situation involving acceleration. F equals ma, a is equal to delta v over delta t, vf squared is equal to vi squared plus 2ad, and so on, and so on, and so on. Well, let's see how easy this stuff really is here, okay? Example 3.5 on 149 says, a lacrosse player exerts an average net horizontal force of 2.8 newtons forward on a 0.14 kilogram lacrosse ball while running with it in the net of a stick. There's a diagram, but we don't really need that. We want to find the acceleration. Okay, it seems pretty easy here. Okay, it seems pretty easy. Let's write down our givens here. Our net force is 2.8 newtons forward, so we'll just make it positive. The mass is 0.14 kilograms. We're looking for the acceleration. Is this Group A or Group B? Is this a Group A problem or a Group B problem? Is this involving constant velocity or does it involve acceleration? Yep. Group B. It involves acceleration, right? Clearly. All right, now we have 6 Group B equations that we're allowed to use now, the 5 that we learned in our last unit and the one that we just learned today. Which one do you want to try? Which one should go first, Haley? Probably the one we learned today, right? F is equal to m times a. We know that a because, well, odds are if we're doing an example problem after just teaching you something, it's probably going to involve what we just taught you. But secondly, if you look at your givens here, I think it's pretty straightforward that this is an F equals ma problem. So F is equal to m times a, or a is equal to F over m, however you want to write it. Let's plug our values in here. 2.8 newtons over the mass of 0.14 kilograms. We do the math there. Works out to be 20. What units would we have here? What units should we have here? Carrie? No, not joules. Good guess, but meters per second squared. It's acceleration, right? What else could you use here, though? We don't usually use this, but we could. It would be valid. Okay. We could use newtons per kilogram as well, right? Because force is newtons and mass is kilograms. Usually we'll stick with meters per second squared. But again, if you put newtons per kilogram, it would be absolutely correct. We got a positive value. We define positive as forward. That means the force here is going to be 20 meters per second squared, or the acceleration, I should say, is 20 meters per second squared forward. It should be, right? Okay, we learned in Newton's second law that the acceleration is proportional to the net force, but also in the same direction. If the force is forward, the acceleration needs to be forward. Good. All right, let's try these 2 questions, please, on 149 and see how easy these ones are, okay? Okay, they're relatively straightforward, right? If we have no problems with those, then we'll move on to the next thing here. We're going to talk now about a few types of forces, right? We're talking about forces. We've talked about how to find the net force, F is equal to m times a. Now let's talk about a few different kinds of forces that we can encounter. Well, there's 3 that we're going to look at today. The first force is a force that you may not have even realized was a force before right now. The first force is what we call weight. The weight of something is the force of gravity acting on that something. Your weight is not 70 kilograms. That's your mass. Your mass is the amount of matter that you possess, and it's going to be the same no matter where you go in the universe. Okay, if you become an astronaut and you go to Mars, your mass will be exactly the same on Mars as it is on Earth. It'll be exactly the same in between here and Mars as it is on Earth. Your mass doesn't change. Okay, it's measured in kilograms. It's the amount of matter that you possess, which of course is going to stay the same anywhere you go. But your weight, the force of gravity that acts on you, does change because the Earth causes different gravity than Mars does. The Earth causes different gravity than the Moon does. Your weight, or the force of gravity that acts on you, depends upon where you are. Depends upon the object that's producing the gravity. Now, how do we find the value of your weight, the force of gravity? Well, normally we're just going to say the force of gravity is equal to m times a, right? The equation we just learned. But specifically, a would be, in the case of the Earth, 9.81 meters per second squared. In the case of the moon, it would be about 1.6 meters per second squared. So a, we sometimes replace with the term g, meaning negative 9.81 or 1.6 or whatever it happens to be, depending upon where you are. Your weight, because it's a force, is measured in newtons. Now, you've always thought your weight was measured in pounds, right? How much do you weigh? 150 pounds, okay, 120 pounds, 170 pounds. Yeah, your weight is measured in pounds. If we look at the old imperial system, just like distance is measured in inches and feet in the old imperial system, just like speed is measured in miles per hour and temperature is measured in degrees Fahrenheit in the old imperial system. If we look at the metric system, the SI system, then your speed is measured in kilometers per hour or meters per second. Your temperature is measured in degrees Celsius. Your weight is measured in newtons because it's a force. That make sense? So your weight is the force of gravity that acts down on you, and as long as you're on the Earth, it acts down on you always. New force, normal force. Probably never heard this one before. Well, in physics, normal tends to mean perpendicular. Perpendicular means 90 degrees. So a normal force would be a force that acts at 90 degrees. 90 degrees to what, though? Typically, it's 90 degrees to the ground, 90 degrees to the surface that you're standing on, but not necessarily. We're going to say it's a force that acts up, but I'm going to put that in quotation marks because it's not always up. The force that acts up at 90 degrees. I should say at 90 degrees to the surface. Well, what does that mean? So I've defined it, but it doesn't really have any real meaning to you right now until I explain it a little bit more. Right now, you're sitting in your desk and not moving. You're in static equilibrium. That's not a new term, right? We've talked about that for the last few days. You're in static equilibrium. That means the forces acting on you must be balanced. Agree? Brian, do you have a force of gravity acting down on you right now? Yes. Yes, you do. Tyler, do you have a force of gravity acting down on you right now? Yes, you do. Seth, do you have a force of gravity acting down on you right now? We all have a force of gravity acting down on us. But the net force acting on you is 0. So if there's a force of gravity acting down on you of, let's say, 700 newtons, then there must also be a force acting up on you of the same value, 700 newtons, right? Otherwise, what would happen? If there was no force acting up on you and there was a force of 700 acting down, what would happen to you? Yeah, you'd be sinking down to the ground, right? Gravity's pulling down on you with 700 newtons. If there was no force acting up on you, you'd be falling. You'd be free falling. Well, that doesn't happen. So there must be a force acting up on you. That force is the force of the floor acting up on you. We call that a normal force. And it pushes up on you at 90 degrees to the surface of the floor. That make sense? Why do we say up in quotation marks, though? Well, if you're standing on the floor like this, okay, it pushes up at 90 degrees. Gravity pulls down. The normal force pushes up at 90 degrees to the surface. But if you're standing on a hill like this, gravity still pulls down, straight down, but the normal force will be up like this at an angle of 90 degrees to the surface. Now, what's important to note about normal force is that when you feel like you weigh a certain weight, you're not feeling your actual weight. You're not feeling gravity pulling you down. You're feeling the normal force. The normal force is your apparent weight. It's how heavy you actually feel. Not how heavy you are, but how heavy you feel. You ever notice sometimes you feel a little bit heavier than you really are, or you feel a little bit lighter than you really are? Give me a situation somewhere that you've experienced, somewhere in the last year, that you feel heavier, even if it's for a brief moment of time, maybe 1 or 2 seconds. Yeah. Okay, roller coaster, sure. When you're going around a loop in a roller coaster, or even around a turn in a roller coaster, sometimes you feel really, really heavy. Or if you go over a bump in a roller coaster, sometimes you feel lighter. Give me another situation of when you feel lighter or heavier than when you really are. Even if you've never ridden a roller coaster because you're afraid to do that, that's okay. You've all done this before. Yeah. Maybe. Certainly all woken up, yes. I'm thinking of something that you've done a little less often than wake up. Swim, all right. Got a couple other issues working there, like buoyant force, right? Going down a hill in a car. Okay, perfect example. When you're going down a hill in a car, sometimes your stomach feels like it goes up into your throat. You feel lighter in that case, right? Situation that I was thinking of is in an elevator, especially an elevator for a really, really tall building, but any elevator you experience this. In 2001, in August of 2001, about a month before the World Trade Center was attacked by 2 airplanes, I was on the roof of the World Trade Center. Literally, I stood on the roof looking out over the city of New York on the World Trade Center. It was 112 stories high. Okay, standing on the roof of a 112-story building. The elevator is fast. Okay, you go up 112 stories, it's a fast elevator. Okay, when you start going upwards, you feel like you're being pushed down hard against the floor. You feel like you're really heavy. And similarly, when you come down from that building, okay, you accelerate down pretty quickly and you feel lighter. Your stomach feels like it's going up into your throat, right? As you accelerate downwards. When do you feel lighter or heavier than you really are? When you accelerate. When you accelerate. When you go over that bump in the car. When you speed up in an airplane. I remember the first time I was ever on an airplane, I was 13 years old. First time I was ever in an airplane. I was by myself. Okay, went around, we're taxiing out onto the runway, going slow like airplanes do when they're taxiing out. And then we turn that corner and all of a sudden we go from about 20 kilometers per hour to about 150 or 200 kilometers per hour almost instantly. And you're pushed back against that seat of the airplane, right? You feel heavy because you're accelerating. You're not heavy. I still weighed the same as I always have, right? I felt heavier because I'm accelerating. Now, in the end, it's the normal force that we feel as a result of that acceleration. Does that make sense? The normal force changes as a result of acceleration. Here's a question for you. Anybody ever gone skydiving by any chance? No? Either have I. It's something that I'd love to do, but I'm not sure that I'll ever have the courage to actually do it. But let's say we did. Let's say we all went skydiving. It's a field trip. We all go skydiving. We jump out of the airplane. We free fall for a few seconds before the parachute opens. As we're free falling, what's the normal force acting on me? How hard is the ground or anything else pushing up on me as I free fall? It isn't. 0, right? How heavy do I feel as I free fall? I feel weightless. Okay, that's weightlessness. The astronauts that are in the International Space Station right now floating around, they're not weightless. They're not weightless. They weigh almost as much as they do on Earth. The force of gravity acting on them, they're only 400 kilometers up. They weigh almost as much as we do right here. But they feel weightless and they appear weightless because they're free falling. The space station and them are free falling. Because of that, there's no normal force acting on them. Because of that, they appear and they feel weightless. So weight The force of gravity is how heavy I really am, but the normal force is how heavy I feel. And it changes as a result of acceleration. Another force, call it the force of friction. It's a resistive force. What does resistive mean? What does resist mean? Goodness, you got to be able to define that for me. Resist or resistive. Yep. Yeah, it goes against something, right? It goes against motion. It's a resistive force that acts between two surfaces. A resistive force that acts between two surfaces. Now, there's two kinds of friction. And we'll talk a lot more detail about the two kinds of friction a little bit later on today. But we'll briefly tell you about them right now. The first kind is called static friction. Oh, you know that word, static, right? What does static mean? It's a two-word definition, a simple two-word definition. What does static mean? Derek, you got it? Not moving. Okay, two-word definition, not moving. Friction involving a not moving object. What? That doesn't make any sense, does it? How can you have friction acting on something that's not moving? What's the friction acting on Leah's desk right now? Zero. What's the friction acting on Leah's desk right now? Is I push her desk, but yet it doesn't move? Something, right? If her desk doesn't move, the forces must be balanced. Well, if I push on it with a force of 10 newtons to the left, then friction must be opposing that with 10 newtons to the right. Static friction is that force that keeps an object from beginning to move. It's an object, it's a friction acting on an object at rest that tries to prevent it from starting to move. We'll say it keeps an object from beginning to move. Or at least it tries to keep an object from beginning to move. Sometimes I might be able to push that desk hard enough where I actually overcome static friction and it moves, right? But it tries to keep it from beginning to move. The other kind of friction is called kinetic friction. Sometimes we call it dynamic friction. Another thing we can call it that you don't really see it named this very often, but it's a good one to help us describe what it really means, sliding friction. It's the friction that resists the motion of an already moving object. So if Leah's desk is at rest, and I give it a push, static friction tries to keep her desk at rest. But if I get it moving, if I overcome static friction and it begins to move, and I push it hard enough that it slides across the room, kinetic or dynamic or sliding friction will cause it to slow down and stop. Okay, it resists the motion of a moving object, of her moving desk. We'll talk a lot more detail about static and kinetic friction a little bit later on, okay? But right now, we just have to know what the basic difference is. One involves moving objects, one involves not moving objects. We should call it translational friction, right? It kind of goes along with our static and translational equilibrium. Okay, a free body diagram is not a force. We've identified our three kinds of forces here already. A free body diagram is not a force. A free body diagram is a picture that we can draw that shows all of the forces acting on an object. So on Leah's desk, for instance, it would show gravity acting down. It would show the normal force acting up. If I was pushing her desk, it would show the force applied by me. Okay, it would show the force of friction that counters my force. It would show all of the forces that act on Leah's desk. It's not a force in itself. It just represents all of the other forces that are acting on it. Let's take a look at a little example here involving a free body diagram and several forces, including different types of forces that are acting here. First one says, the only one says, a free body diagram, draw a free body diagram of a 20-kilogram object that's sliding on a horizontal surface as it's pushed with an applied force of 30 newtons and resisted by a frictional force of 10 newtons. You know what? I don't even know what object this is. Let's make it a box. Just for simplicity, let's make it a box here. It's a 20-kilogram object. Notice I've labeled the mass of the object. I don't technically need to do that for my free body diagram, because a free body diagram isn't a diagram that's designed to show masses. It's a diagram that's designed to show forces. But usually what I end up doing is write all my givens on my free body diagram as well, including masses and anything else that I have. Just because, look, I got to write down my givens anyways. I'm drawing a free body diagram. I might as well just put them down on my diagram. Okay, forces here. It's pushed with an applied force of 30 newtons. I'm going to get one of you guys to come up and draw that. Let's say it's pushed to the right. Okay, we're not told that, but we'll assume that it's pushed to the right. Who wants to come up and draw that applied force of 30 newtons? All right. Take the red pen there. Let's draw that force of 30 newtons. Is he right, guys? Is Aiden right here? Yeah, that's good. That's good. Let's label it as FA is 30 newtons, just so that we remember what force it is, right? Could I have drawn that force over here? FA is 30 newtons. Now, some of you might argue that that's really pulling the object, right, as opposed to pushing the object, but it doesn't really matter because the effect is the same. So if you want to draw where Aiden drew it, that's absolutely fine. If you want to draw it over here where I drew it, that's absolutely fine. Just make sure you don't draw it in both places, because then that's kind of indicating that there's two forces, right? We've got an applied force to the right. Doesn't matter where I draw it, as long as I draw it in the right direction, to the right, 30 newtons. Good. Who's next? We've got a frictional force of 10 newtons. Who's going to come up and draw that one for me? All right, Lewis. Frictional force of 10 newtons. Okay, so Lewis is drawing that frictional force to the left. Is that correct? How did he know that it was to the left as opposed to the right? That's a good question. It doesn't say anywhere that that frictional force is to the left. How did we know that, Bart? Good. Friction is a resistive force, so it's got to oppose the motion. If it's moving to the right as a result of an applied force to the right, then friction's got to be to the left. Now let's label that FF. Does it matter where he draws it, by the way? Usually we'd consider the frictional force to be acting between the surfaces, right? So you'd think you'd draw it down here, but does it really matter? No. He could draw it where he drew it. He could draw it over here. That would be fine. He could draw it over here. It doesn't really matter, as long as he draws it in the right direction. Now, one thing I want to point out here, there's no way really for anybody to have recognized this ahead of time, but there is now. Okay, once I point this out to you. We usually try to draw these forces on the free body diagrams more or less to scale. So that means that the 10 Newton force should be about a third the length of the 30 Newton force. So I'm going to just lengthen my 30 Newton force there. So it's about 3 times as long as my 10 Newton force. It doesn't have to be perfect, just more or less to scale. Is that it? Or are there more forces acting here? There are more. Who's up for the next one? I'm not going to tell you what it is. I'm just going to have you volunteer and come up and draw something else that acts on this. Jacob, come on up. Okay, Jacob's got it. Hardest question so far, right? Because we don't know what that other force is. Okay, so he's labeling gravity downwards as 9.81. You're real close. You're real close, actually. Thank you. Not perfect on that, but you're real close. The force of gravity does act downward. No question about that. We don't know how big that force of gravity is, though. The acceleration due to gravity, Jacob wrote down, was negative 9.81 meters per second squared. But we're not looking to label the acceleration due to gravity. We're looking to label the force. Okay, the force of gravity, we could calculate, but right now we don't know what it is. Let's just label it Fg, acts downward. Now, could he label it down here? Fgx down? Sure he could. It doesn't matter. If we knew how big it was, then we should try to draw it to scale, but right now we don't know how big it is. We could find it pretty easily, but we'll deal with that later on. Is that it? Is there any more? Any more? Okay, Aiden again. Give you the big red pen to draw the last one, Aiden. Oh, is it the last one? Okay, so he's drawn one upwards. What are you going to call that, Aiden? What should we normally call this force? What's the normal thing that we should call this force? Carrie? The normal force, good. Now, what's important to recognize about the normal force here? It acts up 90 degrees, right? But also that in this case, it should be the same value as the force of gravity. And Aiden pretty much drew it the same length already, right? Not sure if it was by coincidence or by design. But the bottom line is this. If this object isn't going up or down, then those forces must balance, gravity and the normal force. They must be the same value. So they should be drawn the same length. The actual weight of this box is 20 times 9.81. How heavy this box feels is the same as the force of gravity in this case, because there's no acceleration. It is only a difference between apparent weight and actual weight. Remember when there's acceleration, we talked about that a few minutes ago. Good? Yep, Bruce? Yeah, you know what? The free body diagram, we technically don't have to calculate anything for the free body diagram. But if we were solving this problem, doing something with this, then yeah, we'd probably have to turn around and calculate the force of gravity. And once we got it, we might as well label it on the diagram there. Yeah. We don't need to do that right now. But again, as part of a bigger question, we probably would. All right, I'm going to have you guys draw a free body diagram now yourselves at your desk. Let's draw a free body diagram for a box that slides down a hill. There's friction acting on the box. We don't know how much friction is. We don't know how heavy the box is. We don't know anything about anything in terms of numbers. But we do now know all of the forces that act on this box. I'm going to draw the hill, and I'm going to draw the box, and I'm going to have you, at your desk, draw all the forces that act on that box. Okay, give you 1 minute, or let's say 2 minutes to do that now. All right, Lewis is going to come up and draw one force for me now that you guys have had a chance to work on this. Just draw one, Lewis, okay? Make sure you label it, though, as to which force you're doing with there, okay? Please label the force of gravity straight down. Is that correct? Is gravity acting straight down when you're on a hill? Absolutely. Gravity always acts straight down toward the center of the earth. Always, 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 always. I'm going to move that, Lewis. Okay, there's no real good reason right now for me to move it, because where you drew it is absolutely correct. It's just later on, a couple weeks from now, you're going to see that it's more convenient to put it where I'm putting it right now. Okay? You put it where you put it, that's absolutely correct. But it becomes more convenient to put it right there. So I'm just going to move it right now. Okay? Yep. Want to do another one? All right. Aiden's up for another one. Aiden and Lewis seem to get these. Can they keep volunteering to put answers up here? Oh, what's he labeling there? He's got a force that's acting kind of up and to the right. What's he going to label this one? What's he labeling it? Fn? That stands for what? Normally it stands for what? Well, the normal force, good. Yeah, it's the normal force. Is he right with that? Absolutely. Is it the same value as the force of gravity? No, it's not. Now, we don't know exactly what that normal force is, but it's not going to be exactly the same value as gravity because it's not directly balancing out gravity here. Normal force is acting up at 90 degrees to the surface, whereas the force of gravity is acting straight down toward the center of the Earth. Anything else here? There is one more force acting here. Stephanie? That's a good question. That's a good question. This is a box, so the surface and the object are parallel, basically, right? But what if they're not? What if it was like a triangular box? Would it be 90 degrees to the surface here, or 90 degrees to the object? What do you think? To the surface. Yeah, it's 90 degrees to the surface right here. Okay, regardless of what the surface of the object is, we care about the surface that the object is riding on. So always 90 degrees to that surface. Good question. One more force. What is it? All right, Jacob. Let's go blue for this one. Switch it up a little bit, Jacob, eh? So he's drawn FF. That's the force of, good, force of friction. It's acting up the hill. Does that make sense? Of course it is. Which way is this box going to go? In the absence of friction, I just let this box go on the hill. Where's it going to go? Down the hill, right? It's going to go down the hill. Well, then, if friction opposes that motion, then friction must act up the hill. What kind of friction is it? Static kinetic friction? Well, we don't know. Okay, we're not told that. Any other forces? Oh, wait. Isn't this one? I'm going to move that, Jacob. Don't have to move it at all. I'm going to move it because I just want to draw something else here right now, and it might get a little cluttered if I keep that where it was. Is that good? Where you had it was just as good. What about this force? What about this mysterious force right here? Let's call it FH, the force of the hill. Doesn't there have to be a hill force pulling it down the hill? Because in the end, if this box is let go freely, where's it going to go? This way, right? Doesn't there have to be a force that way if it moves that way? What do you think? There does have to be a net force acting down the hill. But we're not going to draw it. The reason we're not going to draw it is because that force that pulls it down the hill is really a combination of these two forces. And we're going to learn the vector analysis for that later on in a week or so. But understand that those two forces will combine to give me the force that pulls it down the hill. So we don't need to draw another force that pulls it down the hill. We've already drawn all the forces that pull it down the hill. Does that make sense?